Okay, chemistry, we're on to question number 32 in the winter packet, and what you're being asked to do is write the condensed electron configuration for each of these. However, I want you to add something to this question, and this is required, these additions that I do on this video. So I want you to add the Aufbau for up to the, I'm going to say the 5s subshell. So we're going to start here, and we have the 1s subshell. So again, the way you do this is, I'm going to put this down, is you read this like a book. So the 1s is everything here in the first row. That's the only subshell it has as an s. So it's 1s, and it can hold 2 electrons. Then all the s subshells below that are in these 2 columns, the alkali and alkaline earth metals. So this is the 2s. It can hold 2 electrons. Now you come over to the 2p, and it can hold 6 electrons. Now you come back, go down, and do down a row and back to the left, and you have 3s, and then you have 3p. Come down here is 4s, and then you hit the first D subshell. It's the transition metals are the D subshell. Now the order must be S, P, D, F. You can't change that order. So if this is 4s, it must be followed by the 4p, which is over here, but it's not. It's followed by a D subshell. So who does that D subshell belong to? It has to belong to the 3rd row, because the 3rd row just completed, has actually completed its P subshell. So it's 3s, 4s, 3d. This cannot be 4d, because 4 has not had its P subshell yet. So this is 3d, and then 4p, and then 5s. And I'm going to have you stop right there at 5s. So it's just like reading a book. Okay, the S's are here, except for helium, the one exception. The P's are this block here. The D's are the transition metals, and the F's, which we're not going to deal with, are the rare earth metals down here. Some of these down here. Okay, so let's go ahead and do this. Now what I'm going to have you do first is draw an Aufbau up to 5s. So let's go ahead and do that. So I have 1s. Then next we go down to where lithium and beryllium are, and that's 2s. Then you go to the 2p. So the p is in the 2nd orbital, but it's a slightly higher energy than the 2s. And I should label this x, y, and 2pz. Okay, so each of these can hold 2 electrons. 2 electrons, 2 electrons, 2, 2, and 2. So the p subshell in whole can hold 6 electrons. Now we're ready. The periodic table, we're at the end of 2p. Now whenever you're at the end of a p subshell, you filled a p subshell, you're at a noble gas, and that'll be significant when you're making the condensed electron configuration. Alright, now we're going down to 3s. Okay, so it's here, right there, and that's this one. Now we're going to jump over and we go to 3p is next, just like reading a book. Okay, so now we're at 3p. Now we go to 4s. That puts us right here with potassium and calcium. Now we hit the first D subshell. And since the 4th row has not had its P subshell yet, that won't come until over here, this D subshell must belong to the row before. So just remember the D subshells are the row before. So we're going to draw that over here. And there's 10 elements in the D subshell, so that means you're going to have 5 of these. And you don't have to memorize these, but it's 3D, XY, 3D, YZ, 3D, XZ, and then it's 3D, X squared, Y squared. It's actually minus Y squared. Again, there's no algebra to this, it's just the names, and it's 3D, Z squared. Okay, so those are the names of those 5 subshells. Okay, so now we're at the end of the D here. We're right here, zinc. And now we're ready for the 4p. So we're going to come back here to the p level here. Okay, so that puts us here. Now we're ready for the 5th row. And this is 5s down here, rubidium and strontium. And that's where I told you you can stop here. So we'll stop here, okay, 5s. And again, each of these lines can hold 2 electrons. All right, so let's do O. So I'm going to do these lightly. I'm going to just point to them. So the first electron is going to represent hydrogen, the second one helium, and it's an up arrow and a down arrow. Okay, so I'll do this one here. Up arrow and down arrow. Now you come up to the 2s, which represents lithium and beryllium. Right there. Okay, so now we're ready for the 2p, and that's boron, carbon, nitrogen, and we're going to stop at oxygen because it's asking us for that. So the way you do this, it's called Hund's rule. You don't need to know that. It's up arrow, and then you spread them out. Spread them out. Okay, that gets you 3. You need a 4th one, so that comes back to the first one, and it's a down arrow. Okay, so when they're paired up, they have to be 1 up and 1 down, and then you spread them out first like that. So this is oxygen. So how would you write that? I'm going to write the complete electron configuration here because it's very short. It's going to be 1s2. Again, it's not an s squared. It just means there's 2 electrons in the 1s. In the 2s, there's 2s2. Okay, and then in the third orbital is 3p, and there's 4 electrons there. You don't have to make a distinction between px, py, and pz. It's just 3p4. Okay, so that's the electron configuration for oxygen. Okay, again, let me show you the periodic table. It's 1s2, 2s2, 3p, 1, 2, 3, 4. Now what you do is you go to the noble gas that came in the row before, and you start with that, and then you continue with the next row to do the condensed. So the condensed would look like this. It would start with helium, and that would be this right here. So I'll put a bracket around that. It's the only one where it's an S2. The rest of them are going to be P6s, and you'll see that in the next view. Okay, so it's helium, and then you write the rest of this. 2s2. Okay, that's lithium, beryllium, and 3p4. That's 4 of the elements in the second row p subshell. Okay, so what I'm asking for really is that second one right there. That's the condensed electron configuration. Okay, let's do chlorine. So chlorine, you can just look at the periodic table. It's going to be a 1s2. You always have to start and build your way up. 2s2, 2p6, 3s2, and then it's 3p, 1, 2, 3, 4, 5. Okay? Now, so to write this, we start with the noble gas in the row before. Whenever you have a P6, that's a noble gas. Start in the noble gas in the second row, and then add 3s2 and 3p5. So it's going to be the noble gas in the second row is neon. And that's the condensed electron configuration for chlorine. Okay? Krypton. Okay, it's way down here. It's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d. This is the 3d subshell. 3d10. Count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3d10, and then it's 4p6. Well, you pick the nearest noble gas. Well, it is a noble gas. So all you have to write for krypton is this. You don't have to go back to argon. Okay, some students in the assignment thought you had to do that. You don't have to do that. That's it. That's the condensed electron configuration for krypton. All right, chromium. Let's look at that. Okay, so chromium is right here. So it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then it's going to be 3d1, 2, 3, 4. All right, so, but the condensed is, you're going to start with the noble gas in the row before. So that is right there, argon. So it's going to be Ar, 4s2, and then 3d4. But remember, there's a trick to some of these, and this is one of them. So we're going to start with argon. Okay, and we said the trick to this was that these energy levels are most stable when they're either half filled, and we're talking only about the D. This doesn't apply to the P. It does, but not in this context. Okay, so let's just say it doesn't. So it's 1, 2, 3, 4. So that's 4 of the 10. If you can get it to 5, it'll be more stable. If you get one in there. So what do? You borrow one of the electrons from here. So this becomes 4s1, and this becomes 3d, 1, 2, 3, 4, 5, because 5 makes it half filled. So we're going to go ahead and write that. So we're going to change this. Go ahead and write it like this at first, just to get the hang of it. So this is going to have 5. And where does it get that electron from? It borrows it from the 4s. Okay. 4s is actually considered a higher energy level. It's a little bit odd, but it is. Okay. Okay, there we go. So 4s1, so that's for chromium. Okay. So again, it would have had 2 here, and then 1, 2, 3, 4, and then you borrowed one from here, and you brought it up to here, so you had 1, 2, 3, 4, 5. You half filled the D subshell, and that's a more stable configuration. Okay, let's look at zinc. Zinc's right here. It's at the end of the third of the 3D, and you can let's see. So we're going to get that. Okay, so it already has 10, so it's going to be AR 4s2 3d10. It's already at the end. Okay, so it already has a filled D subshell. It doesn't want to borrow anything. It's happy. Okay, finally molybdenum. Okay, molybdenum is in the 4th row, and you can see it's the 1, 2, 3, 4th element. So if you can add an electron, it'll be halfway filled, and that would make it like technetium. And so it's going to do that. It's going to borrow one from the 5s. So you start with the noble gas in the row before that, which is krypton right there. Okay, and you don't have to do what I'm doing, but as far as this, but I'm going to erase it and change it. That's the way you would think it would be, what I just had. Now it's 5s1, 4d5, so it's a half-filled subshell. So others that would do that are copper. Copper would have 9. If it could add an electron, it would have a filled 3d, so it would borrow it from the 4s. And here's silver. Silver, if it could borrow one, it would be like cadmium, and it would have a 3d10, so it could borrow one from the 5s. Okay? All right. So let's go on with that and draw 2 ways the resonance structure for O3 can be shown. So let's do the Lewis dot structure. So you got oxygen. So again, we're drawing it the standard way. Okay. Line them up. You got 3 oxygens. Now you create octets around everybody. Every terminal atom. Okay, so now you have 16, and you have 8. You need to have 18, so you're going to put 2 more on the lone pair like that. All right. Okay, so now we have that. We have 18, but we don't have an octet, so you're going to take a lone pair from outside. It doesn't matter which side. And we're going to put it right there. So now all of the oxygens have octets. So let's go ahead and write the AX notation for this. And it's 2 bonding domains, this single bond and this double bond, and 1 lone pair. And if you look at your page 15, which you need to have memorized, that's going to be a member of the trigonal planar family. But the actual shape is going to be bent. These are things you need to have memorized. Okay? So that means we can actually redraw it like this. Okay? And I'm going to draw it now with lines. Okay? So I'm going to draw it like this. The single bond there. The central oxygen there. The double bond there. And I'll go ahead and put the lone pairs on. It's just, okay, like that, and you don't use lines for lone pairs. Okay. Alright, so that's what it would look like. It would be a bent molecule. Now, you have a double bond on this side, a single bond on that side. Why? I don't know. It could be on the other side, right? That's what's called a resonance structure. So the two ways to draw that are this. You simply draw this again, or, in fact, I won't draw it again. I'm simply going to draw an arrow, a double arrow between it like that. And now I'm going to draw it again, except I'm going to put the double bond over here. Okay, so that's one way of drawing a resonance structure. The other way is to take the bond order. Now, what is bond order? It's the total number of bonds you see here. So you have a sigma bond. Every bond is a sigma bond. Every single bond is a sigma bond, plus you have a pi bond. So the bond order is the number of actual sigma is sigma, single bonds are sigma, plus pi, double and triple bonds are pi bonds. Sigma plus pi bonds, the number, over bonding domains. That's a place where there's either a single, double, or triple bond. So here you have a double, that's one bonding domain. Here you have a single, that's one bonding domain. So it's going to be, there's one sigma and a pi and another sigma. Sigma, sigma, pi, that's 3. And there's 2 bonding domains, so it equals 1.5. That's the bond order, okay? And we'll practice those some more. I didn't give you other problems in this packet for this, but we'll practice it. So the other way you could draw it, I actually like this way better. First of all, you only have to draw one structure. Is like this. You draw a straight line and then a dashed line. And then here you have a straight line and a dashed line. Okay, and this is 1.5, or you can put 1.5, and this is 1.5. In other words, that extra electron is kind of buzzing, or electrons are actually kind of buzzing around between those two bonds. So those are the two ways you can draw a resonance structure. All right, so be sure you know how to do that. Be sure you know how to calculate bond order. All right. All right, now we're going to do some stoichiometry. First, we did it with just grams to moles, moles to grams, and then later on we did it with gases. Okay, so again, this is the kind of the graphic organizer, the flow chart, but you want to learn to do this without looking at this. You kind of want to have this in your mind. So the only place you have a relationship between this, and this is inside this box. So it's the only place you can go sideways. You can move between them. Up here, liters, and up here in liters you can't. Down here in grams you can't. Okay, here are the molar masses for each of these. So you have to have that. And for gases, it's always the same at standard temperature pressure. And I wrote that that's what this is at, and they'll give that to you if they want you to use this property. But that's 0 degrees centigrade and 1 atmosphere of pressure. Now I realize this is really not going to be a gas, but we're just go with it here, okay? So it is 0 degrees and 1 atmosphere pressure, okay? So any gas at standard temperature pressure is going to be 22.4 liters. So 11 2-liter soda bottles, that's how much, that's a mole of gas. All right, so how many grams of C3H6O are required to create 6.4 liters of CO2? So we're looking for grams of C3H6. That's our question mark. Again, get to where you can do this in your head without looking at this, but I'm doing it in case you still have that issue. And CO2 is here, and it's 6.4 liters. So you start with the number you know, you come down, over, and to the question mark. Some students are still getting it backwards. You don't go from the question mark up to here. You come from what you start with, what you know, come down, over, and over. So our first conversion, our first equivalency is going to be 1 mole equals 22.4 liters of CO2. It's true of any gas, but it's CO2 in this case. Then you're going to move across, and you have what you have is 1 mole of C3H6O equals 3 moles of CO2. So that's the equivalency. You get it straight out of the equation. Okay? And then once you have moles of C3H6O, use the molar mass, 58.09 grams per mole, to get that final answer. So again, we start over here. Learn to structure these types of answers and they won't seem so difficult. Okay, so we're trying to get to grams right there, and we're starting with 6.4 liters. Okay, and its number of arrows is 1, 2, 3. So you're going to need 3 boxes. At this point, you don't have to draw the boxes. Okay, our first equivalency is 1 mole. And it's any gas, but we're dealing with CO2, so we're going to put that down. Okay, we need liters of CO2 to cancel, so liters goes on the bottom. Okay, liters CO2 cancels with liters CO2. Now we're in the equation and we have 1 mole C3H6O equals 3 moles CO2. Okay, and we need, so now we've got our next equivalency from the equation, so we need moles of CO2 to cancel out, so the 3 moles CO2 has to go on the bottom. Okay, moles CO2 cancels. Now we're sitting in this box right here, and we need to come out using the molar mass. So it's 1 mole. Okay. We need moles of C3H6O to cancel out, so we're going to put this one on the bottom. Okay, moles of C3H6O cancels and cancels. Grams of C3H6O is last man standing. That's what's in our answer. So now you go ahead and do the calculation. So I'm going to have you do the calculations. I'll do the first one. You multiply everything on the top. Okay, multiply everything on the box top. So 6.4 times 1 times 1 times 58.06 divided by 22.4 divided by 3 divided by 1. So we'll go ahead and do that. Okay, and I get 5.529. If I'm doing significant figures, I only have 2 right here. I have 3 here and 4 here, but only 2 right there, so it would be 5.5. Remember that when you set moles, that's an ideal number. So you mean exactly 1 mole, exactly 3 moles. So those are not limiting the significant figures. That's an infinite number of significant figures, and so is that. But these are the ones that are measured values, and so they do not, they limit your significant figures. Okay, let's go on. And we're going to first erase this, but try to not use it. Okay, so let's think about this one without looking right now at the graphic organizer. So how many liters of O2? So we're going to have a question mark up in liters above O2. At STP are required to produce 17.84 liters of H2O. So we're going to have to go from 17.84 liters of H2O, we're going to have to come down into the equation to moles of H2O. Then we're going to have to move over to moles of O2, and then we're going to have to move back up to liters of O2. Okay, so try to picture that graphic organizer, however you keep it in your mind. Try to picture that, okay? So again, we're starting from liters of H2O. We're starting from here. We're starting from here. We're coming down to here. Then we're coming across to O2 to there. And then we're going back up to get liters of O2. All right, so let's do that. Start with 17.84. Okay, and our relationship is that for any gas, 1 mole is 22.4 liters. Okay, but it was down, over, and back up, so that's 3 boxes. If you want to still draw boxes, just draw a line if you want. Okay, so there's your equivalency. I need to get down into moles, so I need liters to cancel out. Okay, so liters H2O cancels with liters. Now moles of H2O, so if we look up here in the equation, we have 3 moles of H2O equals 4 moles of O2. Just straight out of the equation. All right, so we need moles of H2O to cancel, so we're going to put moles of H2O on the bottom. Moles of H2O cancels and cancels. So now you're sitting in the moles of H2O. Now you need to get back out, and it's again the conversion 1 mole of O2 equals 22.4 liters of O2. Any gas. Okay, we need moles of O2 to cancel, so this goes on the bottom. Moles of O2 cancels. Last man standing is liters of O2 in the final answer. Okay, so you multiply 17.84 times 1 times 4 times 22.4 divided by 22.4 divided by 3 divided by 1. So you may see right now you could cancel the 22.4 right there and there, okay? And simplify your answer. So go ahead, you do that calculation for that one. Okay, we'll move on. Okay, so how many liters of H2O gas can be produced from 2.25, and that is a decimal there, from 2.25 grams of O2. So let's go back up here again. I'll do this, but try to do it without. So 2.25 grams of O2 is going to be down here underneath O2, and we're trying to get to some type of liters of H2O up here. So we're going to start from here, go up, over, and up again. That's 3 arrows, 3 conversions. Okay, so let's go ahead and write that out here. Okay, there we go. Alrighty, so first we need to go from grams of O2 to moles of O2. So use molar mass, and it's 32 grams per mole. Okay, we need grams to cancel out, so the 32 has to go on the bottom. The other guy goes on top. Okay, grams of O2 cancels and cancels. So now we're sitting inside the equation. We're sitting in moles of O2 right here, and we need to get over to moles of H2O. So it's 4 moles of O2 equals 3 moles of H2O. Okay, we need moles of O2 to cancel, so this one goes on the bottom. Okay, so moles of O2, moles of O2. Alright, finally we need to get from moles of H2O out to liters of H2O. So it's the same relationship for any gas. Okay, we need moles of H2O to cancel, so this one goes on the bottom. Moles of H2O cancels, last man standing is liters of H2O. There it is. So we multiply 2.25 times 1 times 3 times 22.4 divided by 32 divided by 4 divided by 1, and that will give you the answer. Okay, be sure you know how to do these, okay? This is many points on the AP exam. Okay, it's being able to do stoichiometry, and knowing how to organize them and set them up is really the most important thing. All right? Okay. Finally, how many grams of O2 are needed to completely react with 8.92 grams of C3H6O? So we're not even dealing with liters in this one. This is going back to the olden days when we did grams to grams. So it's how many grams of O2 are needed to completely react with 8.92. So in other words, so there's no excess, in other words. That's what it's basically saying. 8.92 grams of this. So you start with the 8.92. You go up using molar mass to get to here. Use the equation, this relationship to get to there, and then come back out using the molar mass for oxygen to get back out here. Okay, so let's go ahead and do that. Oh, right here. And we want to know grams of O2. Okay, and it was 3 conversions, 3 arrows. Okay, so first it's grams of C3H6O to moles. Molar mass. Okay, so we need grams of C3H6O to cancel, so this one goes on the bottom and the mole goes on top. Okay, now for the second equivalency, we come back to the equation. 1 mole of C3H6O equals 4 moles of O2 right there. So 1 mole C3H6O equals 4 moles of O2. Okay, so we have moles of C3H6O, so that one has to go on the bottom. 4 moles O2 on the top. Cancel moles of C3H6O. Okay, now we have to come back out using molar mass of oxygen. Okay, we have moles of O2 on the top, so we need moles of O2 down here. Okay, cancel that and that. Last man standing is grams of O2, which is in our final answer. So you multiply 8.92 times 1 times 4 times 32 divided by 58.09 divided by 1, and that will give you your final answer. Okay, I'm going to wrap this video right here, and we'll move on to the next question on the next video.